So here is some practice with VSEPR geometry and how to approach determining the electron region geometry, but more importantly the molecular geometry, which is the real atoms, and also the bond angles between the atoms. Let's start off with carbon dioxide. So carbon dioxide, if you were to draw the Lewis structure, it would have a total of 6 plus 6 plus 4, which is 16 valence electrons. Drawing it correctly will give you this structure. Oxygen double bonded to carbon, double bonded to oxygen, with lone pair around the oxygen but not the carbon. The electron region geometry can be determined by counting the number of areas around the central atom where there is electron density, such as a lone pair, a single bond, a double bond, or a triple bond. All of those are simply electron regions. There is one electron region, two electron regions around that lone pair. Around that central atom of the carbon. So if I were to make a code system for this, then those two electron regions are broken down into this. There are no lone pair and two bonding areas. The only possible shape where there are no lone pair and two bonding areas would be an electron region geometry that is linear, because it has those two electron regions. And when you take into account only the atoms on the central atom, then those two bond areas are going to also provide a linear molecular geometry. The bond angle between both CO bonds is 180 degrees. And that's how you would do the VSEPR theory as far as the three-dimensional shape, given some information that leads you to first the two-dimensional shape. Selenium dioxide has 18 valence electrons, with selenium in the middle and two oxygens around it. If you bond them once and then do your spreading of your valence, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and of course the 15, 16, 17, 18 that were originally in our bond, we have this as our first step. The selenium only has 6 valence electrons, so in order to create 8, you need to form a double bond with one of the two oxygens, and then remove one of the lone pair as a result. If you count the number of electron regions around that selenium, there is a single bond, which is one region, a lone pair, which is another region, and a double bond, which counts as just one region. Because there are 3 electron regions, it would help us tremendously to code for what they are. There is one lone pair, and there are 2 bonding areas. The electron region geometry that starts off with 3 is going to be Trigonal Planar. If you look at this, this starts off as an electron region geometry of trigonal planar. However, one of the electron regions is a lone pair, and 2 are bond areas. Therefore, the shape that you get when you ignore that lone pair and just think about the effects it has is something that we call bent. So in order to draw selenium dioxide a little bit more realistically, it would be selenium with a lone pair on the top and then 2 oxygen atoms that are arranged in a bent fashion, such as this. The bond angle between the atoms in this molecule are approximately 120. However, each lone pair takes up nearly 2.5 degrees of space, so it's not exact, but it's less than 120 degrees. Even on the AP exam these days, you don't need to give the more precise bond angle when you take into account the lone pair. But the lone pair does take up a lot of room, so it's more like 117-ish degrees. But it does vary even by the specific atoms that are present. Nitrogen trifluoride has 26 valence electrons, and if you do the whole bond one, spread your valence, and then add the remaining valence on the nitrogen, this is the Lewis structure that should result. There is no need for any double bonds. So if we count how many electron regions there are, we have 1, 2, 3, 4. So those 4 electron regions can be broken up into this type of coding. We have 1 lone pair on that nitrogen, and we have 3 bonding areas. The starting shape, or as I sometimes call it, the mother shape, or really the electron region geometry for 4 electron regions, is tetrahedral, which is drawn like this in 3 dimensions. So this is the starting shape, or the electron region geometry, when there are 4 electron regions around that central atom. However, one of our electron regions is actually a lone pair, which means that when we think about our shape, you need to ignore where the lone pair is, because it's going to have its effects on the molecule. And here is where you could draw in your lone pair if you want to, but then go back and think to yourself, well, the electron region geometry is tetrahedral because there are 4 electron regions. But when one of your electron regions is a lone pair, then the leftover shape is the one that we call, for the molecular geometry, trigonal. And then which trigonal is it? Trigonal planar means there are 3 electron regions and they are all bonding areas. Trigonal pyramidal is the one where the atoms are not all in the same plane because there is a lone pair that is pushing or distorting them down. So trigonal pyramidal is the molecular geometry. For a tetrahedral electron geometry, the bond angle is about 109.5. You should definitely know 109.5 degrees for the bond angle in a tetrahedral thing. However, each lone pair takes up about 2.5 degrees of space. Since there is one lone pair, 109.5 minus 2.5 degrees of extra space taken up leaves us with an angle of 107 degrees. However, if you put 109.5 or less than 109.5, you'll be good to go even on the new AP exam. Sulfur dibromide has 20 valence electrons, and if you draw it correctly, it'll have 2 single bonds and 2 lone pair around that sulfur, resulting in 1, 2, 3, 4 electron regions. Those 4 electron regions immediately tell us that it's a tetrahedral electron region geometry. However, if you break it apart into what it is, there are 2 lone pair around that central atom, and there are 2 bonding areas. This will have a shape called bent. And here's why. The molecular geometry is going to be bent, and it stems from the electron region geometry, which is tetrahedral. So if you're looking at this tetrahedral 3D schematic, and you think to yourself, well, there are 2 lone pair, then you can ignore those 2 regions because they are a lone pair. and because they are a lone pair, the leftover shape is bent. So a bent molecule can come from two different possible situations. Either a tetrahedral electron region geometry where there are two lone pair and two bonding areas, or a trigonal planar electron region geometry where there are one lone pair and two bonding areas. The approximate bond angle here is 109.5 for tetrahedral. But remember, for every lone pair, we can take away 2.5 degrees. So minus 2.5 and minus another 2.5, the approximate bond angle is 104.5. However, you could simply write 109.5 as the accepted bond angle. The less than symbol would make it a little bit more appropriate though, because those lone pairs do take up space each. So this was a walkthrough of the second part of VSEPR theory practice, where you have to remember, count your valence, write your Lewis structure, and then think about the derivative it is under the electron region geometry. Sometimes the electron region geometry is the same as a molecular geometry, but if you start adding lone pair and taking off bonding areas, then it starts to create those different shapes.